So let us look at the other way to do it, which is okay. By the way, see, using this smoother kernel also avoids this problem of getting a very discontinuous estimate for the density, because what happens is if you create bins, especially in higher dimensions, given some data, there can be a lot of bins that will not have any data points at all, right, because your data is sparsely sitting in high dimensions. If you construct bins, there can be a lot of bins where you do not even have a single data point. If you smooth it out, then every bin will have some data points, because this every bin now has infinite support, no. So that the density will also be smoothened that way, okay. Okay, so let us look at the next variant of this, which is the nearest neighbor estimates, or here it is a non-parametric density estimate where what did we do in the last case? We fixed V and counted K. Here fix K and grow V, yeah. So we have P is equal to K in V. Okay. Now what you do is in higher dimensions, choose a particular volume and see how many data points have fallen in this particular case, particular volume, okay, and that will give you the density estimate. Now how do you do it in practice? Let us look at one example to do it in practice. How do we actually do it in practice? Now example use case. Let us construct a base classifier with nearest neighbor density estimate for the class conditional density Px given y. Do you understand what I am saying? So we are now constructing a base classifier, okay. To construct a base classifier, we need the class conditional densities to be estimated, and we use nearest neighbor density, non-parametric nearest neighbor density estimate for class condition estimate evaluating the class conditional densities. Do you understand this? Any questions on this? This is very important because algebra is easy, understanding is difficult. Do you see this? Any questions on this? So let us do that now. Okay. Now suppose we want to estimate the class of a sample X. We are given a sample X. What we want to do is estimate the class corresponding to that particular sample. And how does the base classifier do this? See, the analysis that we do right now is sort of connecting all the dots that we have seen so far. So we are constructing a base classifier and we want to get the class of a point X, okay. For that we need to get the posterior of Y given X, this particular X, okay. So let's do that. Now suppose so we place a volume V around X and capture K samples. So we have to create a volume V around this X. So in the nearest neighbor density estimate, non-parametric estimate, what do? Given a point, we want to estimate the density at that point, okay. You keep growing a volume V around that point till you get K points, Okay. Okay. Now suppose we are looking at a binary classification problem. Okay. So let Ki be the number of points within volume V corresponding to the ith class. Correct. So you have a point x, construct a volume around it. So you get k points. Within those k points, let us say k0 are from class 0 and k1 are from class 1. Okay. Now this actually means, in fact it does not have to be a binary classification problem, it can be a k class classification, or okay, k has already been taken, it can be a m class classification problem. Yeah, thanks for the alphabet suggestion. So it can be a m class classification problem. So what happens is, now you have sigma of ki I equal to 1 to m now is equal to k. I will write this example use case is m class classification. We are looking at an m class classification problem. Okay. So this is okay, no, all ki's they sum to 1, sorry, they sum to k, so because there are k points out of which you have k1 from class 1, k2 from class 2 and so on. Okay. Now the nearest neighbor density estimate for the joint density of x and the ith class is given by what? Okay, what are we looking at? We are looking at the nearest neighbor density estimate for the joint distribution of x and yi for the ith class. What is it? So we know that it is k by nv, right? Because we are considering ith class, this will be ki. Does it make sense? So the estimate for the joint density of x and yi, this is the nearest neighbor estimate by the way. So where we have grown a volume, okay, till it encompasses k points. Within those k points, ki are from the ith class. Okay. Okay. Now to construct a base classifier, actually when I started, no, this is a density estimate for p of y given x, not x given y, because the base classifier decides based on p of y given x, right. To construct a base classifier we need p of yi conditioned on x. What is this equal to? This is the joint density divided by the marginal, no? Correct? Is this correct? Yeah. This is equal to what is the denominator? So you take it for all classes, right? Which is k by nv, right? So this is equal to this is what it is. Now what is the final base classifier? This is my base classifier, right? It decides on the ith class if the posterior of the ith class is the highest amongst all posteriors. Okay, this is equal to, take I if correct. Is this correct? All of you with me? Why are you perplexed? We just got the estimate for yi given x, so just writing it that way. So I can leave k, write the class is equal to I if ki is greater than kj. Now what is this? Given a point x, okay, what am I doing? I am taking a volume around x, okay, and seeing how many points in the data set within that volume correspond to the ith class and jth class, and deciding the class of that particular point x as the one, okay, that has the highest appearance within that volume. This is the k nearest neighbor classifier. Okay, this is exactly what is called as the k nearest neighbor classifier.
How do we choose volume?
Using some distance metric. The question is, how do we choose the volume? Okay, given a data point, you look at, in fact, you can choose the volume to be the one that encompasses all the data set, right? Given a data point, okay, look at its neighbors in the entire data set and count how many points corresponding to this ith class and do it. Or okay, you can choose to see, that's why it's called k nearest neighbor, because you can restrict 5, so you can look at 5 nearest neighbors. So take a distance metric, okay, and take that amount of volume that encompasses 5 points. Doesn't matter, 5 points, that is why it's called the 5 nearest neighbors. Okay, construct the volume, okay, such that it encompasses k points, and within those k points construct a base classifier, that's it.
It seems like volume is also a parameter and we are choosing it on our.
K is a parameter. I mean, of course, volume is a parameter through k. See, when you, if you take k to be, let's say 10, then you are implicitly looking at a volume, isn't it? Okay, so here is the punchline. A k nearest neighbor classifier is a base classifier with the density estimate for the joint density of data and labels estimated as the non-parametric density using the nearest neighbor technique. That's what we saw, correct? So what is the nearest neighbor classifier? Given a particular point, it's a non-parametric classifier, right? In the sense that given a particular point, you want to choose its class, fix a k, look at its k closest neighbors and count all classes, right, within those neighbors, and decide the class based on the one that has the highest appearance. That's exactly this base classifier. What are we doing implicitly is that we are constructing a base classifier, okay. To construct a base classifier, we need the density estimates. The density estimates are taken to be non-parametric density estimates, and within the non-parametric density estimate, you choose the nearest neighbor density estimate to estimate the density that is needed to construct a base classifier, and that becomes what is known as a nearest neighbor classifier. Okay. So one way to start an ML course is to start by saying that nearest neighbor classifier is the easiest or the most primitive classifier, okay, that is there. In fact, there is a very powerful result that says that the error, that is error in terms of the risk, okay, that is associated with the nearest neighbor classifier is at most twice that of the base error. That's a result. Okay, I will just state that without proof. You know, this one of the books that I have referred to, this Duda Hart, right, pattern classification, proves this result. What I am saying is that the error, that the true error, the true risk, not the empirical one, the true risk that is associated with a nearest neighbor classifier is at most twice that of the base classifier. So, if you are constructing a hyper complex classification methodology that is doing worse than a nearest neighbor classifier, discard it, because this is the easiest thing that you can do, right? Given some problem, just come, and by the way, you have to choose a distance metric here. Okay, that is a hyperparameter. I mean, you can choose any of your favorite distance metrics. Depending upon your distance metric, you build a k nearest neighbor classifier. Okay, in fact, you can also build a 1 nearest neighbor classifier, where you grow the volume such that you look at the closest point within the data set, and you assign the class of that to this particular data point. That's it. So that's the easiest classifier. So the easiest thing that you can do to solve a classification problem is to construct a nearest neighbor classifier, and nearest neighbor classifier is also a base classifier with this as the density estimate. Okay, this is like deriving known results using unknown concepts. Okay, that's fun actually, right? That's what the abstraction will give you. So every known thing will become a special case of this large family of models that we are looking at. So this completes the density estimation part of this particular course. From the next class, what we will do is we will go back to the ERM worldview, the empirical risk minimization worldview, and I will specifically look at discuss the linear models to start with, the linear family of models from the ERM perspective. Okay, we have already seen that. We have already seen that a linear model with a particular loss function is equivalent to getting a ML estimate for the density with a particular assumption on the class conditional density is what we have seen. We will reinforce that idea. I will talk about the generalized linear models, the so called linear and polynomial regressions, okay, and then we will move on to the regularization, bias variance decomposition and regularization ideas, which is nothing but the map estimate, it is equivalent to the map estimate. So that will end the first lap of this particular course. So we will start with the linear models from the ERM perspective starting next class. Okay, see you in the next class. Thank you.